In the array rotation problem, you're asked to come up with an efficient algorithm to rotate an array on its right by k positions. Let's see what this looks like. We have an array here of 9 elements and k equals 2. You have these two elements that are moved from the back of the array all the way to the front, thereby rotating the array by exactly 2 positions. On LeetCode, there's a few more examples. In this case, you have k equals 3, so you have the last 3 elements in the input array move to the front. You can see this one step at a time by rotating one element at a time. You first rotate the 7, and then you rotated 6, and then you rotated 5, and so you end up having 3 elements up in the front. A second example shows you an array where k equals 2, and the input array has no particular ordering of its elements, so you have the last 2 elements that move up front. So really, the problem is agnostic to the contents of the array. In addition, there's some more requirement. One of them is if you can do this in O of 1 extra space. Really what this means is if you can rotate the array without creating a new array. This is called an in-place rotate. You have to move the items within the same array. Another requirement is that k could be non-negative. That means that k could be 0, or it could be anything greater than 0, including greater than the length of the array. What does that look like? So what does it mean to perform k equals 0 rotations? Well, 0 rotations really means you haven't performed any rotations at all, so the output array should be exactly the same as the input array. Let's see what k equals 8 rotations look like in this array. If k is equal to 8, you would move 8 elements from this array all the way to the front. So you would move 2, 3, 4, 5, 6, 7, 8, 9. The output would be what would k equals 9 look like? K equals 9 is really k equals 8 plus 1. So you would move one more element than the 8th rotation. So you would move the last remaining element, which was 1. And that would mean that the array would be so k equals 9 really looks like k equals 0. With this, we can explore what k equals 10 looks like, where k is greater than the length of the array. The k equals 10 is really k equals 9 plus 1. And if k equals 9 is k equals 0, then k equals 10 is really the same as k equals 1. And the output here is so we can generally say that k is equal to k modulo length of the array. So in this case, if k was 12, this is the same as k equal to 3. And if k was 3, then 3 modulo 9 is still 3. So we want to remember this because it's going to be useful for us when we start coding. There's a really cool trick to understanding this problem, but before that, let's look at something more obvious. And that is, if you reverse an array twice, you're going to get the same array back. Let's pay a closer look at what's going on here. In the first reversal, we're shifting both the position and order of elements. To see that more closely, consider the elements 1, 2, and 3. In the first reversal, the index of these elements have shifted. 1 belongs to index 8, 2 belongs to index 7, and 3 belongs to index 6. And in the second reversal, we recover these back. So 1 goes back to 0, 2 goes back to 1, 3 goes back to 2. Also observe what element precedes which other element. So in the first reversal, we end up shifting the relative ordering of these elements. And you have the ordering 3, 2, and 1. And in the second reversal, you recover these relative orderings and you get back the original ordering, which is 1, 2, and 3. This is obvious, but we'll see why it's important in a moment. Let's go back to the example problem that we started with, where we have an array with numbers 1 through 9 and k equals 2. The output here would be so what has happened is that you have two elements that have moved up front. In the process, the indexes have shifted for every element, but the relative orderings have continued being the same. So the relative orderings for 8 and 9 continue remaining the same here, while the relative orderings for 1 through 7 also remain the same. But the index of every element has definitely shifted. So solving this problem is really about just applying two reversals. The first reversal is applied as usual, and the second reversal is applied at the kth index. Really, you split the array at the kth index and then you reverse the two portions of the array. This recovers the relative orderings of the elements at the two splits. Let's take a look at what the code looks like in this case. Here is some Python code that performs this algorithm. We have a write rotate array function here that takes an array A and a value k. We first downsize k if it was larger than the length of the array. If k was smaller than the length of the array, k remains unchanged. Then we perform the two reversals. The first reversal occurs here, and the second reversal occurs here. The reverse function takes an array and a start and end pointer and promises to reverse elements between the start and end pointer in the array. In the first reversal, we pass the start as 0 and the end as the last element, thereby reversing this entire array. In the second reversal, we call reverse twice, once from between 0 and k minus 1, and the second time from k to the end of the array. The second reversals are performed on these sections when k equals 2, thereby executing our algorithm. The reverse function simply swaps the elements pointed at by start and end and moves start and end towards each other as long as this condition here holds true. Now that you have seen the algorithm and understood the code, I would suggest that you program this in your favorite language and try it on LeetCode.